The next thing I want to discuss is how to prepare a buffer. Will you have to know this or memorize this? No, but it does help you understand how the lab managers prepare buffers and add them to our solutions in the laboratory. Okay, folks? So first, there's 4 different steps that you do to prepare a buffer. You have to choose the conjugate acid-base pair that you want to use. You have to calculate your ratio of your conjugate base and your weak acid using the Henderson-Hasselbalch equation. You can use that, of course. And then you have to determine the buffer concentrations and the mass. Once you have the mass, that's going to be the mass that you're going to mix in the solution to get whatever amount that they're looking for. And then what you can do to correct for pH is simply add drop-wise strong acid or strong base to kind of move the pH in small little amounts and variable amounts so that you get exactly the range you're looking for. So here's an example of a weak acid, and of course it's conjugate base type of buffer solution. So the weak acid will be like acetic acid, Dr. Strange, and of course the conjugate base will be CH3COO minus. That will be considered a buffer solution that a lot of times will be prepared in lab. Another type of buffer solution will be a weak base and its conjugate acid, for example. So say NH3 Iron Man and its conjugate acid NH4 plus can be considered a buffer solution, similar to the type of examples we've seen in our buffer conversation thus far. And I want to show you a quick example of what a preparing a buffer type of question looks like, but I want you to understand you do not need to use this in your homework or even for the exam. It's not something that you need to know. It's just extra information to help you see how these buffers are made or get made in our laboratory portion. So as an example, an environmental chemist needs a carbonate buffer of a pH of 10.00 to study the effects of acid rain on limestone-rich soil. So how many grams of Na2CO3 must she add to 1.5 liters of freshly prepared 0.20 molar NaHCO3 to make the buffer? The Ka of HCO3 minus is 4.7 times 10 to the negative 11. So again, we're trying to prepare a buffer, so we do have the 4 things we want to think of. We want to get the conjugate acid-base pair. We want to make sure we have our ratio of our conjugate base and the weak acid. Then we want to go ahead and get our buffer concentrations and the mass. And then finally, we want to mix the solution and go ahead and get the pH. Okay, folks? So we're kind of using that whole entire schematic to our advantage in this overall example. Now, of course, we have to figure out our conjugate acid-base pair first. They gave us Na2CO3, and we know if it's dissociated, it's going to be 2 Na plus, and then CO3, 2 minus. Na plus doesn't contribute, but CO3, 2 minus can be the conjugate base of a weak acid. What weak acid are we focused on? They already gave us that HC3O minus was weak acid. So when I look at my NaHCO3 here, I know that's going to dissociate to Na plus and HCO3 minus. And so Na plus doesn't matter. And so my conjugate acid-base pair is going to be HCO3 minus and CO3 2 minus. And this is going to be my acid, and this is going to be my base here. Okay, so I have my Henderson-Hasselbalch equation here. And I'm trying to find the ratio of my base to my acid. So I'm going to subtract pKa from both sides. And I get my ratio is equal to pH minus pKa. The pH I'm looking for is 10.00. That was given. I'm going to subtract that by pKa, which is the negative log of my Ka value. My Ka value is 4.7 times 10 to the negative 11. So I get 10.00 minus 10.33. When I subtract those two numbers, I get 0.33. And so therefore, my log of my ratio is equal to 0.33. Now I want to get my ratio by itself. So I take the anti-log, or I take the log of both sides. If I take the log of a log, it's going to cancel. The log of nothing is going to be my anti-log here. And so I have my ratio is equal to 10 raised to a power of negative 0.33. And this is equal to 0.47. So out of my 4 steps, the first step, I already got my conjugate acid-base pair. My second step, I now have my ratio. Now I need to go forward and get my buffer concentrations and, of course, any mass that we're looking for. So what does the ratio equaling 0.47 really mean? It means that for every 1 mole of your weak acid, you're going to get 0.47 moles of your weak base. And so that definitely is going to help us go further and get buffer concentrations and, of course, the mass of our base that we're looking for. Now, how would that work? Well, if I already know my volume and my concentration of my acid, I can get the moles. Once I know the moles, then I can use this as a conversion factor to get the amount of moles of my CO3 2 minus. Once I know the moles of my CO3 2 minus, I can go further and get the gram based on what the question wants. So first I'm going to use my ratio to create my conversion factor. That says for every 0.47 moles of CO3 2 minus, I get 1 mole of HCO3 minus. To get the moles of HCO3 minus, going into step number 3 of what we saw preparing a buffer, I'm going to take my volume and multiply it by my molarity. So 1.5 liters multiplied by 0.20 molar is going to give me 0.30 moles of HCO3 minus, my weak acid. I'm going to take the moles of my weak acid, use my conversion factor to find the moles of my weak base. And so 0.30 multiplied by 0.47 divided by 1 is going to give 0.14 moles of CO3 2 minus. This is going to be my weak base. Now, of course, I have to go further and figure out how many grams of my Na2CO3 must I add to this 1.5 liters of this buffer in order to be able to get the pH of 10.0 that I'm looking for. So let's go ahead and put our moles of CO3 2 minus into grams. So I'm going to take my 0.14 mole of CO3 2 minus, which is the same thing as saying 0.14 mole of Na2CO3, and I'm going to use the molar mass of Na2CO3 to find the grams of Na2CO3. So 0.14 moles multiplied by 105.99 grams of Na2CO3 is going to give me 15 grams of Na2CO3. What does that mean when I'm trying to prepare a buffer? It means I'm first going to take 15 grams of Na2CO3 and I'm going to dissolve it in 1 liter of the 0.20 molar NaHCO3 solution. So for example, say we have this random weirdly shaped flask here, and we're going to add our 15 grams. It's going to dissolve in the 1 liter, and then we're going to increase our amount up to 1.5 liters with that same 0.20 molar NaHCO3 solution or solvent. Okay, folks? Very similar to how we create a solution in the lab. We first get our solid and we dissolve it in whatever the solvent we have. We dissolve it really, really well, and then we're going to go ahead and increase the volume until we hit that meniscus. It's say if we're using a volumetric flask. If you're not using a volumetric flask, up until you get to whatever volume you're looking for. And then after you get to that 1.5 liters, which is the amount of the buffer itself, then you just simply use a pH meter to adjust the pH to 10.00. How do you do that? Well, you're going to simply drop-wise add concentrated strong acid or strong base to get you to be able to decrease the pH or increase the pH. And that's how you would be able to prepare a buffer. And this is how our lab managers prepare buffers in the lab as well. Of course, there's easier ways to go about this. Sometimes you can simply just titrate a weak acid with a strong base, and you automatically have an ability to create a buffer solution. So this is me kind of going back to the previous information, just so you see, hey, this isn't the only way to do it, folks, all right? Of course, we can use the Henderson-Hasselbalch equation to get us through, but there is a way to do it simply by titration as well. And to reiterate, this is not something you have to know. You might have seen flashcard moment, but I tried to make sure that I went ahead and deleted it so that you know that this is not something you have to memorize, know for the exam or anything. It is extra information, and it definitely will help you when you're trying to consider concepts in the lab and really trying to get the details of why these solutions are the way they are.